press the bell icon on the YouTube app and never miss another update.
Good morning, students. In the previous class, we are discussing about the phenomenon of beats in sound. Now, we will start with a new chapter, that is stationary waves. So far, we have discussed about a progressive wave, a wave that travels continuously through a medium without any change in its amplitude, right, in same direction with constant velocity is called as a progressive wave. A progressive wave is produced due to repeated periodic vibrations of particles of a medium. In a progressive wave, all particles of the medium vibrate with same frequency, same period and same amplitude. Right? The main function of a progressive wave is to transport energy from one point to another point. Whenever we say a wave, obviously it is progressive waves. Now we are taking another type of wave, that is a stationary wave. Now before going to take stationary waves, right, let us discuss about reflection of wave. Right. So, we know that a wave can travel in a material medium. I mean, mechanical wave requires a material medium for its propagation. So, when a wave travels from one medium to another medium, right, at the surface separating the two medium, some part of the waves, right, get bounce back to the previous medium, and this phenomenon is called as a reflection of a wave, right. That is when a wave traveling from medium 1 to medium 2, it a part of the wave get bounced back to medium 1. So this phenomenon is called a reflection of wave, right. So generally, when we take the case of light waves, when light waves traveling in air incident on a glass plate, a part of the wave is transmitted through the glass. That phenomenon is called as refraction. There is a change in velocity of light when it travels from one medium to another medium, and is called refraction. At the same time, a part of light is reflected. Right now, the amount of absorption, transmission or reflection, that depends upon the nature of the surface. For example, when light incident on a pure mirror, most of the light get reflected back to the same medium, right. Here this is same, this is true also in the case of mechanical waves or any types of waves, right? Now a wave can be reflected, right, under three conditions. So due to change in medium, that is when it travels from one medium to another medium. Number two, due to change in density of medium, right? So some media are homogeneous media in which density is same at every point of the medium and there is no reflection in that medium. But some media are heterogeneous media where density is different at different parts of the medium. In that case, due to change in density, a wave can be reflected. Now the third one, a wave can be reflected due to change in pressure. Whenever there is a change in pressure in the medium, the wave get reflected back. So under three conditions, a wave can be reflected back. Under suitable conditions, right, there is a nearly 100% reflection, right? So now this concept is very important in understanding stationary waves. So now stationary waves. Now a stationary wave is an experimental technique, right, used to determine wave parameters like frequency, right, wavelength, wave velocity, etc. of a progressive wave, right? Directly, since the particle continuously change their position while vibrating about their mean position, it is difficult to measure the wave parameters. But however, right, with the help of a stationary wave, we can measure frequency, wavelength, wave velocity, etc. of a wave, right? Now what exactly is a stationary wave, right? A stationary wave is formed due to, right, superposition of, right, two identical progressive waves traveling in opposite direction, right? So a stationary wave is formed when two identical progressive waves traveling in opposite directions are superposed on each other. So a stationary wave is formed when two identical progressive waves traveling exactly in opposite direction overlap on each other or superpose on each other. Here identical progressive wave means the two progressive wave should be, right, should have same amplitude, same frequency, same wavelength, same velocity, but they have to travel exactly in opposite direction. But however, it is very difficult to get two separate progressive waves which are identical in all respect. Therefore, to form a stationary wave, a given wave is made to reflect from a point. So under suitable condition, the reflection is nearly 100% and the reflected wave travels opposite to the direct wave. When the reflected wave is made to superpose on the incident wave, right, stationary wave is formed, right. So stationary wave is formed, right. So to form stationary wave, a progressive wave is made to reflect from a point, and reflected wave is made to superpose on incident wave to form stationary wave, right. Now these waves are called stationary waves or standing waves. It is because they do not transport energy and they do not propagate in either direction. Suppose if we have a stretched string fixed at that point, when we move it in up and down direction, so a wave is set up, a transverse wave is set up, it travel along the length of the string. At the fixed point it get reflected, and the reflected wave, right, superposed on, right, the arrow is indicating, right, the direction. This is right. Now these waves, stationary wave formed, does not propagate in either direction. It does not propagate either along the positive x direction or negative x direction. They remains localized, right. The particles vibrate there only, right, and there is no transportation of energy, right. So a stationary wave is called a standing wave because it does not transport either side after the formation due to superposition of two progressive waves are traveling in opposite direction. As a result, they do not transport energy, right. One of the important difference between, right, progressive waves and stationary waves is that progressive waves remains localized, right, a standing wave, and it does not transport energy, right. But a progressive wave continuously propagates through the medium in one direction, and it transfers energy from one point to another point. Then what is the use of stationary wave? It does not transport energy, right. So the stationary waves are not used to transport energy, but they are used, right, as an experimental technique to determine frequency, wavelength, wave velocity, etc. of a wave, right. Now we will take formation of stationary wave. Formation of stationary wave. Now let us consider two identical progressive waves, right, traveling in opposite direction, represented by, right, the displacements y1 and y2, right. Now consider two identical progressive waves traveling in opposite direction. Right. So represented by, now y1 is equal to a sin omega t minus kx, equation 1, right. So this is traveling along positive x direction. Now it is made to reflected from a point, so that it moves along the negative x direction. Now y2 is equal to a sin omega t plus kx, equation 2. This is traveling along negative x direction, right. So the wave y1 is equal to a sin omega t minus kx, where omega is equal to 2 pi f, right, angular frequency, and f is frequency, right. K is propagation constant, k is equal to 2 pi by lambda, we know that. Now the negative sign here in this equation indicates that the first wave is traveling along positive x direction. Here positive sign indicates that the second wave is traveling along negative x direction. When they superposed on each other, now according to principle of superposition of wave, the resultant displacement of a particle, right, is this is equal to y1 plus y2, or y is equal to y1, this is a sin omega t minus kx, plus y2 a sin omega t plus kx, or y is equal to, taking a common, sin omega t minus kx plus a means sin omega t plus kx, right. Now using this formula, trigonometric formula, sin a plus sin b is equal to, right, 2 sin a plus b by 2 cos a minus b by 2, using this formula, right. Now we have y is equal to, this is 2 into a, 2a, right. Now this is a omega t minus kx plus omega t plus kx by 2 into cos omega t minus kx, here again minus of this one, minus omega t plus kx. This is omega t minus kx minus omega t plus kx by 2. Here plus omega means plus minus kx means minus omega t minus into minus, this is minus into plus, this is minus kx. Here omega t get cancelled, here kx get cancelled, so we left with y is equal to 2a, right. This is, we take it as sin 2a sine omega t by 2, this get cancelled, 2 to cos, right, minus kx minus kx, minus 2kx divided by 2 minus kx, but cos minus theta is equal to cos theta, this is equal to cos kx, or y is equal to 2a cos kx into sin omega t. Let us take it as equation 3. This is the equation of a stationary wave. Remember, the equation of progressive wave, generally y is equal to a sin omega t minus kx, right? Here the equation of a progressive wave is y is equal to 2a cos kx sin omega t, where a is amplitude of the component waves, k is propagation constant 2 pi by lambda, omega is, right, the angular frequency, x is position of the particle, right? So y gives the displacement of a particle at a distance x at any instant of time t, right? This is how we can obtain the equation of a stationary wave. Now we have obtained equation of stationary wave. Y is equal to 2a cos kx sin omega t, where 2a cos kx is a resultant amplitude of stationary wave. Now we have resultant amplitude of stationary wave, resultant amplitude of stationary wave, that say, let us represent it by r. So r is equal to 2a cos kx. It is because any wave equation is of the form, right, y is equal to a sin omega t. A wave equation is the product of amplitude and sine function. So here there is a sine function sin omega t, and the remaining every term on the right hand side except sin omega t represents amplitude, right? So it is clear that this amplitude, right, here a is constant, k is constant, right? So this indicates that the resultant amplitude of stationary wave, right, depends upon position of the particle. That means in progressive waves all particles will have the same amplitude, but in a stationary waves, right, different particles will have, right, different amplitude depending upon the position x, right? So it is clear resultant amplitude depends upon position of the particle. Now case 1. So when that x is equal to, we will take some position 0, lambda by 2, lambda, 3 lambda by 2, etc. is equal to n lambda by 2, where n is an integer like 0, 1, 2, 3, etc. Right? We put n is equal to 0, we get 0. N is equal to 1, lambda by 2. N is equal to 2, 2 lambda by 2, lambda. N is equal to 3, 3 lambda by 4, etc. Now we have cos, we have this value of kx is equal to, right, k 2 pi by lambda into this is n lambda by 2 2 get cancel, lambda get cancel, that is equal to n pi, right? That is equal to 0, pi, 2 pi, 3 pi, etc. n pi. So for, right, cos n pi. Now cos n pi is equal to plus or minus 1. Cos 0, 2 pi, 4 pi, 6 pi, etc. it becomes plus 1. Pi, 3 pi, etc. becomes minus 1. Therefore, now the resultant amplitude is maximum, and that is equal to, right, 2 plus or minus 2e, right? Now the particles which are at distances 0, lambda by 2, lambda, 3 lambda by 2, etc. Suppose if lambda is taken to be equal to 1 meter, then particles at position 0, lambda by 2, 0.5 meter, lambda 1 meter, 1.5 meter, 2 meter, 2.5 meter, etc. will have maximum amplitude, and such particles are called antinodes, that is represented by n. So for particles x is equal to 0, lambda by 2, lambda, 3 lambda by 2, etc. they have maximum resultant amplitude of vibration, and those particles are called, right, nodes, right, sorry, antinode. Those particles are called antinodes. Now case 2, when x is equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, etc. is equal to 2n plus 1 lambda by 4. Suppose if lambda is taken to be 1 meter, then it is 0.25 meter, 0.75 meter, 1.25 meter, 1.75 meter, etc. Right? For those particles, we have kx is equal to 2 pi by lambda into, right, 2n plus 1, right, lambda by 4, right. So this lambda get cancelled, that we will get, this is equal to 2n plus 1 pi by 2, that is, you put n is equal to 0, this is pi by 2, n is equal to 1, 3 pi by 2, n is equal to 3, 5 pi by 2, etc. So for all these values, cos pi by 2, cos 3 pi by 2, cos pi by 2 is 0, right. Therefore here, so cos, right, kx is equal to, right, cos, right, 2n plus 1 pi by 2 is equal to 0. Therefore, the resultant amplitude is minimum here. For all the values of x satisfying these values, right, now the cos kx becomes 0, and that amplitude becomes 0 resultant. That means these particles do not vibrate. They are permanently at rest. They are permanently at rest, and such particles are called nodes, and this is n. So these stationary waves are characterized by alternate nodes and antinodes, right. Now, so we have obtained the condition. Right. Now, A stationary wave can be represented like this. Right. Now, these particles, right, I have marked here, they are always at rest and they are called nodes. Right. Now, these particles, what I am pointing out, are vibrating with maximum amplitude and they are called antinodes. They are called antinodes. So here when I write that amplitude of different particles here, it can be represented like that. Right. See here. Now the amplitude of particle at node is 0. For the next particle, right, it has some value. So as amplitude goes on moving up to antinode, the amplitude increases and maximum. From antinode to node, amplitude decreases, right, and becomes minimum. But this does not happen in progressive wave. In progressive wave, all the particles vibrate with right, same amplitude, right, but here the vibrates with different amplitude, right. Now we have, for the value of x is equal to 0, lambda by 4, lambda by 2, 3 lambda by 4, lambda, right, 5 lambda by 4, 3 lambda by 2, etc. So here we have antinode, node, antinode, node, antinode, node, right, antinode, right. That means in a stationary waves, nodes and antinodes occur alternately. At 0, antinode, next lambda by 4, right, node, next antinode, node, antinodes are formed here. Now, a node, right, node is a particle in a medium, right, which is always at rest due to a stationary wave. So antinode, represented by the abbreviation AN, antinode is a particle of a medium which vibrates with maximum amplitude due to a stationary wave. Nodes and antinodes always occur, right, alternately. Now when we take this as a progressive wave, direct wave, then these 2 points represents the successive crest and the distance between, right, here, this is right, equal to lambda, not distance between 2 successive antinodes. I have taken these 2 points. Therefore, the distance between 2 antinodes is lambda by 2. The distance between 2 successive nodes is lambda by 2, and the distance between a node and an immediate antinode is lambda by 4. So, in a stationary wave, the distance between 2 successive antinodes is lambda by 2. 2 successive nodes is again lambda by 2, but the distance between a node and an immediate antinode is lambda by 4. You should remember that one. Distances, they are very important. when we are going to discuss the modes of vibration in stretched string and in ear columns, right? And another important thing is here the region of space between two successive nodes is called as a segment or loop. A segment or loop. It is a region of space between two successive nodes. This is one segment, two segment, three segment, four segment, five segments. So in the figure, the medium is divided into five segments, right? Therefore, when a stationary wave is formed in a medium, the medium is divided into several number of loops or segment. Now, what is the distance between two nodes, right? This is equal to lambda by 2. Therefore, right, so here length of segment, that is equal to distance between two nodes, which is equal to lambda by 2. The distance between the two nodes or a segment is lambda by 2. Now see here, when we consider the particles in a loop, all the particles, right, they move in upward direction at any given instant of time. At that instant of time, the particles in the neighboring loop, right, they are moving downward direction. Now here the particles are moving in upward direction, here downward direction, here again upward direction, right? So in any given loop, all the particles vibrate with the same phase. They reach their extreme position at the same time, they reach their mean position at the same time, they have same phase. But when we consider the particles in adjacent loops or neighboring loops, they have a phase difference of pi or 180 degree, because the moment when the particles in one loop are moving in upward direction, that's the same moment the particles in the next adjacent loop, right, starts moving in a vertically downward direction, right? So a stationary wave is formed, right, due to superposition of two identical progressive wave traveling in opposite directions. Number two, stationary waves do not propagate along either direction, they remain localized. Number three, right, they do not transport energy. Number four, amplitude is different for different particles. It is maximum at antinodes and minimum at nodes, right? The region of space between two nodes of a stationary wave is called as segment or loop. Length of a segment or loop is equal to lambda by 2, where lambda is a wavelength of stationary wave, right? The wavelength lambda of stationary wave is same as the wavelength of the component wave. Distance between two successive nodes and two successive antinodes is lambda by 2, but the distance between two nodes and antinodes, right, in a node and an immediate antinode is lambda by 4, right? Now that's all about the formation of stationary wave. Stationary waves are extremely used, right, to determine frequency, wavelength, wave velocity, etc. of a progressive wave by forming stationary wave. Now, we'll take comparison between stationary wave and progressive wave. Now, number one, progressive wave is set up by continuous vibrations of particles of the medium, whereas stationary wave, right, is formed due to superposition of two identical progressive waves traveling in opposite direction. Progressive waves travel with constant speed in a medium. Stationary waves do not propagate along either direction. Number three, progressive wave, they transport energy from one place to another place, but progressive waves, stationary waves do not transport energy from one place to another place, right? Now, fourth one, in progressive wave, no particle of the medium is permanently at rest. But in stationary wave, certain particles at nodes are permanently at rest. And in progressive wave, amplitude of vibration is the same for all the particles. In stationary wave, amplitude is different for different particles. It is maximum at antinode and minimum at node. Next, phase of particles in progressive wave varies continuously with time. The phase of a particle changes. But in a stationary wave, the phase of in a given segment, the phase of all particle is same. However, the phase of the particles in neighboring loops are different, and all the particles, right, in progressive wave reach their extreme position and simul position and mean position at different instants of time. But in a stationary wave, all particles reach their extreme position or mean position simultaneously at the same time. Now, the equation of progressive wave, y is equal to a sin omega t minus kx, and equation of stationary wave, y is equal to 2a cos kx into sin omega t. Now, these are all the comparison. And one more thing, now at nodes, the velocity of simple harmonic motion and amplitude of vibration are 0, but pressure is maximum at nodes. Remember, at nodes, velocity of vibration, that is simple harmonic motion, is 0 because particle is at rest. Amplitude is 0 because particle is at rest, but the pressure is maximum, right? But at extreme position, right, amplitude is maximum, velocity of simple harmonic motion is maximum, and pressure is minimum, right? So, a progressive wave is characterized by a series of crescent troughs, whereas a stationary wave is characterized by a series of alternate nodes and antinodes. A stationary wave may be a longitudinal stationary wave if it is formed due to superposition of two longitudinal waves, or a stationary wave may be a transverse stationary wave. It may be formed due to the superposition of two transverse waves traveling in opposite direction. So far we have discussed reflection of wave, formation of stationary waves, right, obtained expression for, right, resultant displacement of particles in a stationary wave, expression for resultant amplitude. We have discussed condition for maximum amplitude. The points are called antinodes, right. The condition for, right, minimum amplitude or zero, those points are called as nodes, right. And then we have discussed the characteristics of stationary waves, right, that I have explained after nodes and antinodes. Then we have compared, right, the stationary waves, that means properties of progressive waves and stationary wave. Now that's all about this class. Then in the next class we will take modes of vibration in stretched string and modes of vibration in ear column. Okay, we will continue in the next class.